Thank you very much, Andrea, and thank you very much for staying late because you're in Europe. Um, and now, next in lines are Stefan and Bob.
All right, so we're not going to be showing anything cool, and everyone can see my screen, I assume? Yeah, good, okay. So we're not going to be showing anything cool, and GraphQL tools are actually quite interesting for anyone who has to deal with them. Any help we can get there is super helpful, so that was really neat, Andrea. Bobby and I are going to talk about existential sadness, but at a light evening pace. So we're going to go through some of the top 4 vulnerabilities that we see in Golang projects that we'd really like developers to stop having. And my name is Stefan Edwards. I am the practice lead for commercial services here at Trail of Bits. You can find me basically anywhere as Logical. I'm joined by Bobby Tonic. He's a senior AppSec engineer here. Twitter handle Bobby Tables, and he's on GitHub as btonic. And we both work at Trail of Bits. Bobby and I, although I run commercial services, Bobby and I also work together in our AppSec subgroup as well. So we see a lot of Go. We worked on the Kubernetes threat model and technical review together. We've done a number of blockchains, that sort of thing. So we see a lot of Go code, and we see a lot of these problems over and over again. And so what I wanted to actually go through tonight were just 4 really simple things that we see in Go continuously. These are integers and numerics, and we'll also point to some work that Nico has done in integers with CodeQL. So integers and numeric, some standard library nuances that we see very frequently that people are unaware of, error checking and type assertions, and then defer semantics. So we'll be swapping back and forth going through each of these. And we want to show you what these problems are, how to find them, and most importantly, how to fix them so that we can stop seeing them in our code and other auditors can stop seeing them as well. And if you take anything away from this talk, it's the fact that Go has some nuances and there's some edge cases that people are really not expecting to see when they're working with them. I think there's a lot of interesting things, especially around numerics and around error handling and whatnot, that they're not unintuitive, but they may not be the first thing that you think of whenever you hop into a Go code base. And I think a number of these are actually fairly easily uncovered. There's nothing really tricky about these. There's nothing really dense about these, but if you're unaware of them, you may not actually be looking for them when you're writing Go or when you're auditing Go yourself. And we give hints to Go tooling, and I think most people have seen Go's tooling can be complex and hit or miss, but we do give some hints into what we use for tooling and the sorts of things that we do to look for these things. So it makes sense for everyone? So Go's integers are actually fascinating. When this code is somewhat taken from Kubernetes itself. This is something that Bobby actually discovered during the assessment. And the thing that we very frequently see is that, you know, integers in Go are actually machine width, but they are not necessarily typed in the way that most people expect. So on a 32-bit machine, you may have an int, but an int is actually 32 bits wide. And so the semantics of how strconv a to I work are actually dependent on which machine it's being run on. So the first code snippet here, and I use this in our Go security class and whatnot as a gotcha, like who can guess what this does? It actually depends on which machine you run this on. So 32-bit wide machine, there's actually truncation before it's turned into an integer, and then the conversion to an int32 works as you would expect, save for it's truncated, so it's a different value than you may expect. And on 64-bit machines, there's actually a downcast, and you have a truncation there as well. So Bobby actually noticed this in kubectl on the client side, and was able to bypass some of the things that we were expecting kubectl to do as we were looking through integer numerics. So the takeaway is just that integers are not exactly what people expect in Go, apparently, since we see these issues effectively everywhere. And again, it may seem very obvious, but we've seen this across projects in CNCF. We've seen this in blockchains that we worked in. We've seen this in web applications, etc. So while everyone on the call may may think of this as quite normal, or may think of this as obvious, we see it quite frequently. And so the one thing I think most people probably should avoid as much as possible is strconf A to I is almost certainly wrong for the code that you're working on. There are certain cases where it makes sense. You don't care necessarily what precision of the integer you're working on. You don't care about, you're not actually worried about overflows or those sorts of things. But for the most part, you probably should not be using strconf A to I. And you should always audit flows from parseInt or parseuint to a different type. So one of the things that we saw and then Nico automated with CodeQL was to find flows that went from something with parseInt to an int32. And I actually wanted to call out the one, we did not catch this during our assessment, but Nico actually caught this with CodeQL. I simplified it for this talk, but basically someone was attempting to parse like scientific notation using parseInt and then ended up downcasting it afterwards. So they ended up with different widths here. You can see they're parsing for 64, but then they're downcasting to 32. So that just whenever you see these sorts of flows, whenever you see anything going from a integer parseInt, 64 bits wide, etc., down to 32-bit or anything there, just check those flows. And so effectively anything with a naked int type on it, an int without a precision after it, is probably something that you want to look into. The other thing that we always ask when we're doing these sorts of assessments are, what platform are you actually compiling this on? Because very frequently we have customers that don't fence things for AMD 64 or for another system and then allow it to be built on a 32-bit system, which has the incorrect semantics. And aside from checking your data flows from strconf, parseInt, or parseuint, you effectively want to use, you effectively always want to use parseInt for these and avoid A to I. And Nico can talk to this probably later during breakout sessions, but CodeQL has been very interesting for hunting these sorts of things down for us as well. So we do a lot of this manually, but CodeQL itself can actually handle these things. So a very interesting thing, also a very small thing, but we'd really prefer that people stop using integers and whatnot in these ways. So Bobby, you want to take it away?
Sure. So I'm going to kind of switch the topic just a little bit to focus on like the things that are there and that we use almost every day. So standard libraries are effectively the building blocks of like most software, right? And in theory, they should avoid exposing abusable behavior. But this doesn't typically happen, even in standard libraries. And so a quick example of this one is the os.makeDarAll and ioutil.writefile. I think you also have like os.openFile and these types of things, right? They'll effectively populate directories or create a file or open file handles and those types of things. But specifically, it will populate a directory, right? So in the os.makeDarAll situation, it'll populate a directory if it already isn't there. But if it is there, well, if you could go down to the next slide real quick. Yeah. So basically, populating the directories, if they don't already exist, is a very important detail, mostly because you can pass the particular mode that they need to be created with, right? But what happens if some of the directories in the path exist, but with different permissions than what you specified, right? That is a very granular detail that often we see people forget, right? And it might not necessarily be intuitive at first. When you think about it, it's like, oh, well, if I specify a path with a given set of permissions, then it should just create that path with those permissions. But if they already exist, then what if it breaks something along that path, right? So it's not intuitive at first. When you look deeper into it, it's even weirder. And this is also to note that the same type of thing happens with like writing a file and those types of things. What if the file already exists? And to kind of sprinkle it on top, this is all before UMask is applied. So the real kicker here is like you need to be checking your permissions for whether they are held before you make them, after you make them, because there are lots of different factors that could come and effectively do something that you didn't want it to do. Like a UMask, you think that you're creating a file with a particular permission set, it's not. Like, does the directory already exist with a different set of permissions? Yes, then it's not going to make it with that. So an attacker can effectively use this through pre-population attacks, right? If they know that a particular file with sensitive information is going to be at a particular location and the program hasn't run yet, they can just pre-populate it with overly permissive permissions. And thus, when you go in and actually tail said file, you could potentially see sensitive information. So for example, in the Kubernetes assessment, right? There were creds in logs if you had debugging enabled. That's not a good thing, but an attacker could potentially use that to get access to other things. Next slide.
And the other thing too, we've seen the thing where we've seen OS make dir all abused quite frequently as well is the assumption that the file system, it will return error if something exists. So we're going to write keys to a specific location, and now your private keys are owned by someone else who they shouldn't be owned to. And it's a great segue into errors in general in Go, right? If you've worked with Go, errors are an interesting beast. They're slightly different from what you may expect in other languages. And we see a number of continuous issues with them. And I've listed 4 here, but someone might take me to task that there's actually only 3 of these on here. And we can obviously discuss that at the end of this. But in terms of how Go's error handling works, we see these sorts of patterns continuously. Someone accidentally assigns to error twice within 2 assignments. They use a type assertion without an OK check, or they do the wrong thing with error. So Bobby and I were on an assessment just recently where someone was accidentally checking that error is equal to nil and doing something rather than not equal to nil. And those just simple logic handling in here, simple understanding of what your data flow is, can lead to a very different section of your code. So we actually see quite a few type assertion issues and panics, especially around network parsing code. We do a large number of blockchain assessments here at Trail of Bits. A lot of the work that we do is bespoke blockchains. And so one of the first things that we actually look through always is just a simple error check, and often with asserts, to see where we can actually pull through code bases and look for areas that look like there's a type assertion that may be user controlled, maybe something that we would be interested in, and then start to attack it from there. Now, you'll also note that I'm suggesting that you use inf-assign. The reason why, if you're a code auditor or if you are hunting for bugs and you have this sort of thing, Go itself will not complain if you assign to error twice. So very often we see areas where error handling meant to check the first error, and then an issue or more code was written, and we forgot to check the return value there, and the program continues. So these 3, error check and inf-assign, are probably our bog standard, besides just using our 2 fists to find these sorts of things. And the other thing too, and this goes for any type of security testing, please fuzz the stuffing out of everything that you're doing, especially if you have network parsing code. We find a lot of very simple low-hanging fruit just with Redomsa or Fuzzatron or those sorts of fuzzers, even against Go code or Rust code itself. So we can find these things relatively quick just with very simple and low-hanging fruit checkers like error check and inf-assign. So whenever you're writing code, or if you're auditing code, just check that all errors are actually handled rigorously. There's a number of areas in Go itself where there are certain things that seem to be handled but aren't, and it's very simple to miss an error check or shoot yourself in the foot with something there. Really, the compiler won't save you. You do have to have things like GoSec and GoVet and other tools on hand. And as much as possible, try to avoid type assertions. I understand that if you're doing serialization or you're doing certain other techniques, you have to use this. And if you do, always make sure that you are checking that okay is true. There's a number of locations where Bobby and I have landed exploits, and others on our team, of course, have landed things just by someone using a type conversion, and now we have a panic from a very simple attacker controlled position. So it's a very simple pattern, and I think it flows into what Bobby wanted to talk about next, which is something Bobby specializes in.
Yeah, so effectively, defer is crucial in a lot of the exception handling in Go, right? You know, you have the typical defer, panic, recover approach, and this is all fine and dandy, right? Sometimes you might defer a resource.close or a resource.finish to clean something up after you use it in a particular function scope, and that's great. But there are some areas that could effectively lead you down the wrong path as far as its semantics go. Go to the next slide. So when deferring a function, the values returned are often ignored, including error values. So for example, if you open a file to write to it, right, and you defer file.close, that will effectively run after that function body has completed, but before the return. And say you might have, you know, maybe you wrote a bunch of content into it and the buffer hasn't yet entirely written, or there was an error when flushing to disk or similar, right? Because you deferred that file.close, you will not be able to recover that error value. It is effectively lost in the void. No panic will occur because of it. It just kind of happens. Furthermore, say you call .finish on something, and .finish is only ever supposed to be executed once, but you accidentally put your defer inside of a loop, right? You might have used multiple of these resources. And so now you actually won't cause an exception during your function body, but instead during the defer stack, when you are popping that particular stack and you call finish twice, now you panic, and that gets raised to parent scope, kinda, if you can go to the next slide. So when deferring a function, the order of that defer stack matters. So if you panic in a deferred function, it can be recovered by a deferred function earlier in that defer stack. So say you knew that a particular function could potentially panic. So you defer appropriately, right? Put a recover, cool. But that recover happens maybe in an inner loop of a nested loop. And so it doesn't actually necessarily match up, right? You might have one extra call that panics, and there is no recover above it on that stack. So when that is executed, effectively that gets raised to the parent caller. So it is effectively an unhandled exception. Furthermore, the panic semantics are also weird, and I'll kind of leave that to the reader's disclosure. The hint, can you go up one more slide real quick? So at the bottom, there's actually some fun goodness that can come from the recover semantics, specifically its return value. Next slide. Yeah. So effectively, to kind of prevent a lot of these types of issues, because there are also more that are not on that slide, just avoid deferring functions that return an error value. You should explicitly check them in almost every case. If you are going to enumerate the values that are passed to panic, there are lots of weird bugs that can happen when you pass nil to panic. So effectively, if you maybe switched up your variables, right? And instead of error, you have your expected variable, and you pass that as the panic because you're like, okay, cool, it's going to have a message. Not necessarily. And that can actually break almost every recover case. And then finally, review the specification. Specifically, the defer semantics are super, super granular because a lot of people have run into these issues. Pass by copy versus pass by reference. When you actually invoke the defer statement is super important. Understanding when the defer statement actually executes before return. and a bunch of other different scoping rules for like inline functions. All these things matter because they are easy things to mess up on. The Go compiler will not save you from a lot of these issues.
And Bobby hates it when I say this, but defer and whatnot are effectively delimited continuations if you're familiar with that PLT semantic. Or unwind, protect, and whatnot in Lisp. But this is actually part of a larger talk that I gave. It's my Kyoto School of Go nihilism. So if you want to see more of these, there's a bunch there. But thank you very much, everyone. If you have questions, we can take them in chat because I know we're running on time. So, but thanks, everyone.